In the vast, dark theater of space, black holes play the role of cosmic executioners, pulling in light, matter, and even time itself with their unmatched gravitational grip. They're a testament to how extreme the universe can be. The final chapters in the lives of massive stars. Scientists believed they understood their behavior, their origins, and their limits. But in a shocking twist, one black hole didn't just bend space, it shattered expectations. This black hole, later dubbed LB1, wasn't supposed to exist. At least, not in the way we found it. According to everything we knew about stellar evolution, LB1's characteristics were theoretically impossible. And yet, it was there, defying the laws of physics, or, rather, showing us that those laws might not be complete. A brief history of black holes before diving into the anomaly. Let's understand what black holes are. When a massive star reaches the end of its life, it undergoes a supernova explosion. What remains is the star's dense core. If this remnant is massive enough, typically more than 3 times the mass of our sun, it collapses into a singularity, a point of infinite density, surrounded by an event horizon, beyond which nothing escapes. Black holes come in several flavors. Stellar mass black holes, formed from the collapse of massive stars, usually between 5 and 50 times the mass of the sun. Intermediate mass black holes, rare and not fully understood. They range from hundreds to thousands of solar mass. Supermassive black holes, giants residing in galactic centers, millions or billions of times more massive than the sun. These categories have been extensively studied. Observations, simulations, and theoretical models have aligned around the idea that there's an upper limit to the mass a stellar black hole can achieve from a single star's collapse. That's due to a phenomenon known as parent stability supernova, where very massive stars don't leave any black hole behind at all. The observation that changed everything in 2019. A team of Chinese scientists using the Large Sky Area Multi-Object Fiber Spectroscopic Telescope detected something strange. They had been surveying stars that orbited invisible companions, likely black holes, and one star stood out. It was orbiting an object with a mass of approximately 70 solar. Let's be clear, according to astrophysical models, that shouldn't be possible. A black hole of that size, born from a star in our galaxy's environment, should not exist. Yet the evidence was strong. The team double-checked their data. The orbital motion of the visible star, the velocity curves, and follow-up spectroscopy all pointed to the same conclusion. Something impossibly massive and invisible was tugging on that star. This was LB1. How the black hole was found? Unlike black holes in binary systems that emit X-rays by siphoning matter from a companion, LB1 was quiet. It wasn't drawing in matter visibly, which made it a stealthy target. Instead, astronomers used a method similar to how planets are discovered by observing the wobble of the visible star. Lamost observed that the star was moving in a periodic fashion, indicating it was being gravitationally influenced by an unseen partner. By studying the movement of this star over several months, scientists derived the mass of the companion object. It wasn't a neutron star or white dwarf. The numbers pointed to a black hole but one, with a mass far exceeding the predicted maximum. Why it shouldn't exist? Here's where it gets interesting. A star that massive enough to create a 70 solar mass black hole should self-destruct entirely in a parent stability supernova. In such explosions, the gamma rays in the star's core produce electron-positron pairs that reduce the pressure, leading to collapse and a runaway thermonuclear explosion that completely obliterates the star. No remnant, no black hole, just dispersed elements. Yet LB1 was there, with mass estimates that directly contradicted this. Was our understanding of these extreme supernova flawed? Was this object formed through an entirely different process? Or was it not born from a single star at all? Global shockwaves in the scientific community. The discovery rippled across the scientific world. Some extraordinary claims require extraordinary evidence, and this was no exception. Criticism focused on the interpretation of the visible star's motion and the assumptions used in calculating the black hole's mass. Subsequent studies suggested the mass might be closer to 10 to 20 solar masses within the expected range. But even with more conservative estimates, LB1 challenged the norms. Whether or not LB1 turned out to be as massive as initially reported, the mere possibility reignited interest in re-evaluating black hole formation models. Were there other rogue giants hiding in the cosmos? Could we be missing entire categories of stellar remnants because they don't emit radiation in ways we were used to detecting? Other impossible black holes. LB1 isn't the only black hole to challenge existing models. In 2020, the LIGO and Virgo gravitational wave observatories detected a merger of 2 black holes, one of them weighing about 85 solar mass. Again, this falls within the forbidden mass gap where parent stability supernova are expected to prevent black hole formation. This event, named GW1-90521, created a new black hole around 142 solar massista, first definitive observation of an intermediate mass black hole. But more importantly, it confirmed that black holes in the mass gap do exist. Whether formed by stellar collapse or mergers of smaller black holes, nature clearly finds ways around our theoretical limitations. A glimpse into the unknown, the existence of black holes like LB1 and GW190521 doesn't just raise questions, it opens doors. Perhaps there are conditions in the universe we've never imagined. Maybe in regions of low metallicity, such as in the early universe or specific parts of our galaxy, massive stars lose less mass and collapse more efficiently. Or maybe we're seeing the aftereffects of previous black hole mergers. Each possibility rewrites a piece of our cosmic playbook. The humbling of modern science. Science is built on the foundation of models' mathematical descriptions of how we believe nature works. These models are tested, refined, and sometimes overthrown. The black hole that shouldn't exist is a perfect reminder that our understanding of the cosmos is still young. For every answer we find, the universe offers 10 new questions. LB1, whether it ends up being a 70 solar mass monster or something slightly more modest, serves as a cosmic puzzle piece that doesn't quite fit. But that's exactly why it's so important. It forces scientists to dig deeper, to question assumptions, and to open their minds to new possibilities. What happens next? In the chapters to follow, we'll explore how this anomaly has inspired a rethinking of black hole physics, the theoretical models being torn apart and rebuilt, and the thrilling search for more impossible objects. One discovery has the power to reshape everything we think we know about stellar death, gravitational collapse, and the very structure of space. This is not the story of a mistake or an exception. It's the story of science doing what it does best, growing, and LB1 is just the beginning. The rise of a new scientific frontier. When the story of LB1 and other black holes in the forbidden mass gap emerged, it ignited a new era of exploration. This wasn't just about tweaking old models. This was a call to action for the world's brightest minds and most powerful machines. Suddenly, observatories around the globe began turning their gaze to the stars with a new purpose. To find more of these cosmic rebels, a worldwide effort begins. Black hole research shifted from quiet niche work to high-stakes, scientific racing. Every major space agency and observatory network began prioritizing black hole surveys. China's Lemnos telescope, which had found LB1, expanded its surveys to hunt for similar stellar companions with unusual orbital patterns. NASA and ESA strengthened data analysis pipelines for the transiting exoplanet survey, satellite, and the Gaia Space Observatory, looking not just for planets, but for stars, wobbling due to unseen massive companions. Ground-based observatories like Keck, VLT, and SALT launched dedicated observing campaigns to previously cataloged stars for overlooked signs of black hole interactions. Gravitational wave observatories including LIGO Virgo and CAGRA accelerated improvements in sensitivity and signal triangulation, hoping to catch more black hole mergers in the mass gap. Every new detection mattered. Each unexpected signal had the potential to rewrite what we knew about the universe. Data mining the cosmos, while telescopes scanned the skies, teams of astrophysicists, computer scientists, and AI experts began combing through archival data. The question they asked was simple. What else have we missed? It turned out a lot. In decades of astronomical data, there were dozens of overlooked systems showing irregular light curves, unexpected Doppler shifts, or inexplicably heavy invisible companions. Machine learning algorithms trained on LB1-like profiles began flagging these systems for One example was a binary star system cataloged in 1999 that had been ignored due to data noise. When reprocessed with modern tools, the system revealed an orbital motion consistent with a 55 solar mass black hole. Another potential candidate came from X-ray archives, where weak but regular emissions pointed to a massive dormant object briefly feeding on stellar wind. The realization was sobering. LB1 may not be rare. We just hadn't known how to look. Beyond Earth, eyes in space in the search for answers. Earthbound telescopes have limits. Atmospheric distortion, light pollution, and the rotational cycle of the planet mean gaps in coverage. So, humanity turned to space. James Webb Space Telescope, although primarily built for deep space exploration and studying the early universe, JWST's infrared sensitivity allowed it to peer into dense star-forming regions. It began identifying possible intermediate black holes by observing stellar motion distortions in distant star clusters. The Laser Interferometer Space Antenna, set for launch in the 2030s, LISA is a joint ESA-NASA mission that will detect gravitational waves from space. Unlike LIGO, which is limited by terrestrial noise, LISA will be able to detect low-frequency waves from massive black hole mergers, including those from the early universe. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years. It will provide wide-field surveys capable of identifying countless stellar objects and systems behaving in ways only explained by hidden massive partners. Each mission had different strengths, but together they formed a coordinated strike force, probing the universe's deepest mysteries. Artificial intelligence joins the hunt. I wasn't just an aid, it became a core part of the black hole hunt. Trained on millions of light curves, gravitational wave templates, and stellar motion signatures, neural networks could sift through more data in hours than human astronomers could in years. These models identified likely black hole candidates, predicted gravitational wave signals before they occurred based on galactic binary distributions, simulated the life cycles of massive stars under dozens of environmental variables to estimate how often rogue black holes might form. AI also began generating alternative explanations for certain anomalies, which led scientists to revise observing strategies. It was less a case of man versus machine, and more man and machine versus the cosmic unknown. Citizen science. The public joins in unexpectedly. The black hole search began capturing the public imagination. Online platforms like Zooniverse launched projects, inviting volunteers to analyze stellar data for irregular. Thousands of amateur astronomers, students, and enthusiasts joined in, with surprising success. One such citizen, a 17-year-old student in Australia, identified a stellar system with peculiar light fluctuations. This led professionals to confirm it was a likely black hole with over 60 solar masses, another data point in the mass gap. Media outlets began referring to this as the black hole gold rush, and rightly so. Never before had such a broad coalition of minds, professional and amateur alike, been united in pursuit of the unseen. Rewriting the star maps as new candidates were confirmed, a new challenge emerged. Updating our star maps. In the Milky Way alone, models previously predicted 100 million stellar black holes. But if high-mass black holes were more common than assumed, that number could be even higher. Worse, the most massive ones could be distorting stellar dynamics in ways we hadn't accounted for. Some star clusters were rotating oddly. Some galaxies had asymmetrical shapes that now seemed explainable by the presence of massive rogue black holes at their periphery. The gravity maps of nearby galaxies had to be redrawn. Every dark corner, every silent sector, was now a potential hiding place for objects we never thought could exist. Astrophysics gets political with scientific interests. Came funding, and with funding, national space agencies began vying for prestige. China launched follow-up missions to study binary star systems in the galactic disk. The U.S. boosted NASA's budget for black hole detection missions. The EU prioritized gravitational wave satellites. There was even talk of a global black hole tracking network, akin to weather satellites, combining optical, radio, and gravitational wave observatories in real time. The goal? To monitor suspected rogue black holes as they moved. Some policymakers asked a more ominous question. What if one of these massive black holes was wandering toward us? A cosmic threat? While the chance of Earth being consumed by a rogue black hole is infinitesimally small, it's not zero. More pressing was the need to understand how often massive black holes interact with their environments. Could a wandering black hole pass through a solar system, stripping planets of orbits? Could it trigger gamma-ray bursts, or distort the space around it in dangerous ways? Simulations began modeling potential interactions between rogue black holes and planetary systems. While none predicted immediate threats, the realization was clear. We were living in a universe with more massive, silent predators than we had imagined. Looking ahead, Chapter 3 is not about answers. It's about the hunt. The black hole that shouldn't exist opened a Pandora's box of questions. In response, the global scientific community rose together, blending technology, collaboration, and curiosity in pursuit of clarity. The data's flowing, the theories are shifting, the boundaries are breaking, and somewhere out there, hidden in the gravitational shadows, is the next impossible black hole.